Hey, welcome everybody. 5.3 and 5.4. They're both kind of similar, shorter sections. So I'm going to kind of throw them both at the same time here. So first of all, 5.3 deals with our sum and difference identities. Okay, so the sum and difference identities are going to be in front of you when you do this video. So I'm not going to write them all down. So what you're going to want to look at is down at the bottom left-hand side of your paper, the sum and difference identities. You'll notice that we have one for sine, actually two for sine, two for cosine, and two for tangent, basically split up between the sum and the difference, two different identities. But they're ones that actually will be helpful if you were to memorize them. And I know I say memorize a lot, but this particular thing, this particular chapter, it's always useful to memorize some of your identities so you don't have to always go back to your identity paper. All right, so the way we can do these two particular questions using the sum and difference identity, let's first just start with saying, okay, let's say I had the sine of, A. Well, let's not use A. I don't want to use A. Let's use the, how can I do this? Let's say the sine of 100 plus the, not sine, sine of 100 plus 10. Well, this tells me it's a sum inside the sine, which tells me it's got to be the sine of the first one times the cosine of the second plus the sine of the second times the cosine of the first one. Now that doesn't really help me in this particular question because I don't know what the sine of 100 is or the cosine of 10. And if I was just going to use the calculator here, I might as well just have used the calculator back here. But in this particular question here, the first one, the tangent of 15, what I want to do is I want to be able to write this as the tangent of the sum or difference of two special angles. So basically, I'm asking, hey, what's the exact value? I don't care what the stupid decimal approximation of this is anymore. And I'm going to say, okay, tangent of 15. Well, doing a little math, I could say, well, that's actually a tangent of 45 degrees minus 30 degrees, which tells me I need the difference of a tangent. So the difference of a tangent is going to be tangent of the first one minus tangent of the second one divided by 1 plus tangent of the first times the tangent of the second. You got to remember these are all degrees. Well, the tangent of 45. Oh, now we're going to find some exact answers because these are nice special angles. The tangent of 45 degrees is 1. The tangent of 30 degrees is root 3 over 3. And 1 plus 1 times root 3 over 3. And I get, okay, 3 minus root 3 over 3. Remember, combine your fractions, combine your denominators, or find common denominators. And then 3 plus radical 3 over 3. When I flip and multiply, sorry, I have to come all the way to the left of the page. I kind of went this in the wrong direction here. When I flip and multiply, those bottom 3's are going to cancel, and I get 3 minus radical 3 over 3 plus radical 3. And some of you are saying, I hope he stops right there, but I'm not going to because I want you to actually simplify this. I'm going to multiply by 3 minus radical 3 and 3 minus radical 3. You remember conjugates get rid of the radicals there. So I get 9 minus 6 radical 3 plus 3 all over 9 minus 3. So I get a nice and lovely 12 minus 6 radical 3 all over 6. And I get 2 minus radical 3. As long as I didn't make any errors there, we should get 2 minus radical 3. All right, so notice if you plug this in your calculator, you should probably get 2 minus radical 3, which is a decimal approximation for tangent 15 degrees. All right, what about sine of 11 pi twelfths? Well, 11, I know 11 is 5 plus 6, so let's hope that 5 plus 6 makes a little bit of sense here. It's sine of 5 pi twelfths plus 6 pi twelfths. No, that doesn't help at all. Darn, 5 pi twelfths just doesn't work. Darn. What about, I don't know. Well, I do know. Don't worry about this. What if I had some sort of fourths and thirds? These ones are hard, right? And you're trying to split up 11 pi twelfths being the sum of two different things. Does that get it? Pi fourths plus pi thirds? That's going to be 4 plus 3. That's 7. It's close. What about 2 pi thirds? Well, this is going to be 3 pi twelfths plus, what, 8 pi 12? Oh, look, 11. You see, even I had to think about it a little bit, so I need pi fourths and 2 pi thirds. All right, so sine of, and guys, obviously you could have changed this to a degree and figured out a very nice sum, but I like to do these with fractions. I like to make things a little bit more challenging for myself. So pi fourths plus 2 pi thirds, and now I have a sign of a sum, so I can say, okay, it's the sine of pi fourths times the cosine of 2 pi thirds plus the sine of 2 pi thirds, not plus, times the cosine of pi fourths. Now it's super simple. Sine of pi fourths, root 2 over 2. Cosine of 2 pi thirds. Well, if you find that on your circle there, it is negative 1/2 plus sine of 2 pi thirds, root 3 over 2, times the cosine, which is root 2 over 2. So I do a little simplifying here. I get negative radical 2 over 4 plus radical 6 over 4. And obviously you can combine this, I guess, if we wanted to here. We could say negative radical 2 plus radical 6 all over 4. And we get this nice, lovely answer. By the way, you'll notice a lot of these numbers show up a lot, like radical 2s and radical 6 and radical 3s and all those sort of numbers, because that's kind of your only choices, right? Radical 2 over 2, radical 3 over 2, radical 2 over 2, 1/2. It's really only your only choices. All right. I could do the other direction here, and obviously this is just kind of a just a practice is using the sum and difference identities. I look at this particular first one here, and I say, okay, sine times cosine minus cosine times sine. And I look at this, and it tells me that it's got to be sine of u minus v. Well, u being the first degree and v being the second degree, I get the sine of 42 minus 17 is the sine of 25? Well, I can't figure that answer out, so that's as far as we go. Just write the expression as the sine, cosine, or tangent of an angle. All right, next one. I look at sine of x times sine of 2x minus cosine x cosine 2x. Well, if I have sine and cosine together, that automatically tells me it's got to be the cosine of something. And because it's a minus, it tells me it's actually the sum inside my cosine. So it actually becomes the cosine of x plus 2x. And don't leave that, because that's obviously cosine of 3x. And you're done. That's it. But one of the useful areas for this is actually looking at the sine of 2x. And the sine of 2x could be written as the sine of x plus the sine of x. Or, sorry, my fault. No, that's not true. Sine of x plus x. And you could actually write this as, let's say, okay, sine x cosine x plus sine x cosine x. And I get 2 sine x cosine x. Very useful one. This actually ends up being one of our angles or one of our identities in a few minutes here, actually. So kind of keep that in the back of the mind. We can rewrite 2x as the sum of x plus x. All right, where are we going to go here? We're going to prove, and you'll notice that this is one of our, actually it's not our cofunction identity. I mistake there. That's not our cofunction, because our cofunction says plus pi halves, not pi. All right, so using the sum identity for sine, I can say sine of x cosine of pi plus sine of pi cosine of x. And I can do some simplifying. Cosine of pi is going to be 0, so I get sine x times 0 plus the sine of pi, or sorry, cosine of pi is not 0, goofball. Man, where's my head here? Cosine of pi is -1, and the sine of pi is 0. And I get -1 times sine is negative sine of x, and 0 times cosine is just 0. So, oh, look at that. We just proved it. We just did a proof. All right, same idea for the next one here. Let's just use the cosine of a sum. So cosine x, cosine 3 pi halves, minus sine x, sine 3 pi halves. And you look here and you go, okay, well, cosine of 3 pi halves is 0. Pretty sure I got this one right this time. Minus sine of 3 pi halves is -1. And negative sine of x times -1 is plus sine of x. That becomes 0 for the other piece. And you get sine of x and check mark, done. You'll notice a lot of these proofs are really not too challenging for sum and difference identities, but they're good ones to know. These are all good ones. All right, so moving on to 5.4, these are our multiple angle identities. So if you're getting something like the sine of 2x, or the sine of x over 2, or actually we don't deal too much with the power reducing, but it's in there anyway. Let's take a look at what this is going to look like. So this is section 5.4. If you didn't see this big screen that says 5.4 on it, or little screen if you're watching on your phone for some reason. All right, so let's use these identities here. Prove these two statements are equal. Now, here's the thing. This is the double angle identity. But I want to prove that it's true, and I want to use the sum identity to prove that it's true, kind of like I said just a couple minutes ago. I want to rewrite this as cosine of x plus x, and I can rewrite that as cosine x minus sine x sine x. Well, cosine x times cosine x is cosine squared. And you notice I get cosine squared minus sine squared. Well, here's where the idea of the proofs come in. You need to know where to go. I need to go to cosines only. So I want to get rid of this sine squared. Well, I know just off the top of my head that sine squared is actually equal to 1 minus cosine squared x. Which means I then get cosine squared x minus 1 plus, because minus minus, cosine squared of x. And look at there, I get 2 cosine squared x minus 1. Oh, look, there we go, we proved it. What about cosine of cosine of 6x? Now, this proof, you don't want to split this up into a whole bunch of sums. Not really, anyway. So what I want to do is I want to actually now use the double angle identity for cosine. Well, the double angle identity says if I have the cosine of two somethings. Well, in this case, I can say it's actually 2 times 3x. Right? Because 6x is 2 times 3x. So I can say this is actually equal to, that's actually it, right? Because it tells me my double angle identity says cosine of 2 somethings. So in this case, the cosine of 2u is equal to 2 cosine squared u minus 1. Well, in this case, my u is just 3x. So I'm just going to go straight ahead and say, okay, well, that's just 2 cosine squared 3x minus 1 because the 3x was really my u to begin with. Oops. All right, let's find all solutions. Now, this is kind of a new thing for us, finding all solutions. Oh, this looks challenging. All right, so let's see what this is going to say. Here we're solving, by the way. Notice there's an equal sign. It doesn't say prove. So we're going to actually solve. Well, in order to solve these equations, it's usually a little bit easier if both of the signs are kind of the same. But notice I have a double angle and a single angle. So what I want to do is I want to get rid of this double angle, and I know how to do that using my double angle identity. Sine of 2x is actually equal to 2 sine of x cosine of x. So I'm going to say it's equal to sine of x. Now, because we are solving this equation, I can subtract 2 sine of x from both sides and set it equal to 0. Well, now we're just getting into these ideas of, oh, I can just factor and set both pieces equal to 0. So I can say, okay, 2 sine of x equals 0. And I can say cosine of x minus 1 equals 0. And here's where things get tricky. So I'm going to say, okay, sine of x equals to 0, and here cosine of x is equal to 1. All right, so x is equal to, well, where is sine equal to 0? Sine is equal to 0, at pi, at 2 pi. It's actually, if you keep going around the circle, just continue. It's 3 pi, and 4 pi, and 5 pi. And I don't want to keep writing because I'm going to be here forever. And I could go negative. I could go in the other direction. So what I want to do here is, when it says find all solutions, now there's going to be a couple different questions here. When I say find all solutions, that means write an expression that will get an answer for every single one. Now, if you notice that if I had this this thing 0, pi, 2 pi, 3 pi, dot, dot, dot. And if I went backwards, negative pi, negative 2 pi, dot, dot, dot. This is going to continue, and I could write this as, starting with the smallest one, 0, plus, I just want to see how far apart are these all. I noticed that all of them are pi units apart. They have a common difference of pi. So I'm going to say pi, common difference is kind of like slope, n. So n is my variable. And notice n could be any number. If I plug in a 1, I get pi. If I plug in a 7, I get 7 pi. It's part of the answer. And you could simplify this answer to n pi. Now that's all solutions. That's every single one of them. Same thing goes for cosine of x equals to 1. Well, cosine of x is equal to 1 at 0, at, it's 2 pi, and continuing around, I get, 4 pi? And so on and so forth. That means I can represent this. The common difference between them all is 2 pi. So I'm going to say it's actually 2n pi, putting the variable wherever I feel like it here. Or you could say 2 pi n, or n 2 pi, I guess, if you really want to. The other way this question is going to be slightly varied is saying find all solutions on the interval from 0 to 2 pi. That's just wants all of the answers on one circle, not on 2 circles and 6 circles and infinitely many circles. All right? But I don't like dealing with both of them at the same time here. Okay, what else do I have here? What about cosine squared plus cosine equals cosine of 2x? Well, same idea goes here. I don't really want this double angle at all. But I do want everything in the same variable. So if I look at my double angle for cosine, I have 3 variations. And I want the one that only says cosine in it because I want us to keep everything the same. So I'm going to say this is actually 2 cosine squared of x minus 1. I'm just going to rewrite that. And then I can do the same thing I did before, and because it's an equation, I can say this is actually 2 cosine, sorry, not 2 cosine squared. If I subtract cosine squared from both sides, I get cosine squared x minus cosine x minus 1 equals 0. Well, this doesn't look very nice. And you might have had to graph this particular version, or I even wrote the problem down wrong. Who knows anymore, right? Let's change this to a 2 right here to make this a possible problem. And actually, I think I want to do that. I want to change this to a... shoot. I kind of messed this problem up, didn't I? Let's change this... Oh, goodness. I wrote a bad problem here. Hate it when I do that. And because I'm mid-video, I can't really rewrite this one. So we're going to scratch this one. And we're going to look at a different problem here. We'll come back to a different problem where we can factor. All right, I want to use the half angle identity on this next one, and I want to find the exact value. So up here at the top, I'm going to say, okay, tangent of 195 degrees is actually equal to tangent of what? It's something over 2. Well, if I just multiplied this by 2, I get 383.90. And the half angle identity for tangent is kind of ugly, and you're like, well, which one should I use? I don't know. Use the easier one. I wouldn't use the square root one, really, but you can. So let's think about this for a minute. So let's try, you should get the same thing from both of them, you'll notice. Let's just try the first nicer one here. Oh, heck with it. Let's just live dangerous. Let's use the square root one. So my u in this case is 390. And if you don't know where 390 is, 390 has a coterminal angle to 30 degrees in quadrant 1. Well, in quadrant 1, cosine of 30 degrees is root 3 over 2. You get kind of something ugly here, but it's not too bad. 1 minus radical 3 over 2, or sorry, 2 minus, over 2 plus radical 3 over 2. That's my fraction here being simplified. I'm going to have to erase some stuff because I wasn't paying attention to space on my screen. Silly goofball. All right, so I get 2 minus radical 3 over 2 minus radical 3 over 2 plus radical 3. I'm still under the square root, don't forget. And if you simplified this like before, I have to multiply by 2 minus radical 3. So I get 4 and a plus 3, which makes 7, minus 4 radicals of 3, all over 4 minus 3, which is 1. Well, that's nice because it kind of goes away, right? And the big thing here is you're going to get equals to plus or minus the square root of 7 minus 4 radicals of 3, all under a radical, but you have to figure out, is it positive or negative? And here's where you have to come back to the original question. Tangent of 195. Well, you have to look, what quadrant is that in? Tangent of 195. 195 is in quadrant 3, and tangent's positive, so I want the positive answer here. So you can never forget about quadrants. You always have to think about quadrants here. Especially for tangent, because tangent's kind of goofy sometimes. All right, so I know I gave you this assignment sheet already. What I do want to talk about is something I could actually factor. Let's say you had something like cosine squared x plus 3 cosine x plus 2 equals to 0. Let's say that's something you came up with here using some of your identities. And this factors to cosine x plus 2 and cosine x plus 1. And there's some things that come up with this. So if you said cosine of x equals negative 2, cosine of x equals negative 1, you'll notice that cosine of x is never negative 2. So there's no solution on this side. And cosine of x here equals negative 1. This is when x is equal to pi. Now if I said, hey, find all of your answers on the interval from 0 to 2 pi. If I said, hey, find all the answers on one circle, that would be this. But in this case, if I said, hey, find all solutions, the only other times that cosine is negative 1 is 1 full period away. And it's every 1 period away, so 2n pi. So I'm just going to keep going by 2 pi, 2 pi, 2 pi, 2 pi, 2 pi, 2 pi. All right, so make sure you know how to factor quadratics. Very useful. You could obviously use some quadratic formula, but that gets kind of ugly. All right, so you have your assignment sheet. you remember I did 2 lessons here, so kind of getting through this chapter 5 a little bit quick so we can really study it and really focus on it rather than focusing on the videos. All right, so have fun with this. I will see you guys later.